Welcome back to AUTS. In this video, we'll be going over dual incline pulleys, where there's two inclines and both with different angles, or they could be the same, but usually with different angles. A pulley at the top, and you have to decide which way the system moves and what direction it accelerates. So these are relatively, straightforward, as in not to solve, but its concept is the same, right? Draw free body diagrams and then always just make equations out of them, find a system of equations, and then solve for acceleration and other forces, whatever you need. Okay, if I gave you that this weight was 100 newtons and this weight was 50 newtons, okay, then if I asked you what would be the acceleration first, you'd have to do one step before anything else, okay? You'd have to find W sine theta, which is the weight sine theta, and since there's no other force acting here, no friction, then you would see which W sine theta was greater, okay? Which force was greater, because that's the only force driving friction, right? Driving acceleration. So if this one is greater, then the system will accelerate in this way. If this one is greater, the system will accelerate in this way. Okay, so it's a bit different, as in you have to find out what those are and you have to work accordingly. Okay, so like I did, right? Let me draw the diagram again so you can see. But we have a 53-degree angle here, okay? Pulley here. The block we have here has a weight. So not a mass, a weight of 100 newtons. Oh, that's the other block. This one has a weight of 50 newtons. And the block over here has a weight of 100 newtons with an angle of 30 degrees. Okay? So how do you compare these and how do you find out which direction it's going to accelerate? Well, weight is just mg, right? So instead of doing mg sine theta, I already know what mg is. So I can just do weight times sine theta. 100 newtons times sine of 30 degrees. That's the only force driving me, because the tensions cancel out, in overall they cancel out across the rope. And then the mg cosine theta cancels out with the normal in both blocks, right? So mg sine theta is what is driving my force on both sides. So this would be 50 newtons. And 50 newtons times sine of 53, which is mg times sine of 53, is about 39.93 newtons. Okay? And since 50 newtons is greater than 39.93, the system is going to accelerate this way. Okay, so the 100 newton weight is going to go downward and the 50 newton weight is going to go upward. Okay, it's pretty simple. Block 1 slides down, block 2 is pulled up. Then you can set up the acceleration equations. Okay, now let me just draw the diagram again. So this is 50 newtons, 53 degrees, weight of 100 newtons at 30 degrees. Okay, and if I look at the free body diagram for each one of them, this one, since it's accelerating downward, let me call that negative, okay? So mg sine theta, which is the only acceleration driver here, right? 100 newtons times sine of 30 degrees is equal to the net force here, right? And that's net force is going to be mass times acceleration, Newton's second law. So it's going to be 50 newtons is equal to mass, which we don't know, but we're going to find out, right? So 100 newtons is equal to mg, that's the weight. So since m is equal to 9.1, 100 newtons divided by 9.1 is equal to m. So meter per second squared, right? M is not equal to 9.1, sorry. M divided 100 newtons divided by G is equal to M. So that should give us around 10.19 kgs. Okay. Now this is 10.19 kgs times acceleration. And if I'm going to call this negative, then I can call this negative, right? Because they're both going in the downward direction here. But if they're both negative, then it doesn't really matter. I can delete these and cancel them. So that's one of my equations. But what you want to remember is that's not the only part of my equation, right? What's the other part of my equation? That was only the mg sine theta. I also have tension pulling it upward. So then the negatives do matter. Okay? So tension, let me just say tension is upward, right? And upward is a positive direction. 50 newtons is going downward here. So 50 times sine, 100 times sine of 30, right? Downward. Mg sine theta is downward. So then negative 10.19 kg times acceleration, because this is going to also be going downward, right? So that's why I make that acceleration negative, because I know it's going to go downward. So I can then put the negative sign here. For the 50 Newton weight, so tension here is also trying to drag it upward, okay? But it's mg sine theta, which is 39.93. It's trying to drag it downward. And then that's equal to the mass's acceleration, which is, so first let me find out m, right? M times A. So 50 newtons is equal to 9.81 meter per second squared times m. M is equal to 50 divided by 9.81, or 5.0, approximately 5.1 kgs. Okay, so T minus 39.93 newtons is equal to 5.1 kgs times acceleration. And then I can take this equation here. Tension minus 50 newtons is equal to 10.19 kgs times acceleration. I can subtract them. And this acceleration is going to be positive, right? That's why I'm not going to put a negative here. I mean, this is negative, but this is going in the positive direction. That's why I'm not going to put a negative, because I defined positive as, upward as positive, right? And we know this block is going upward when we initially deduced that. So that's why it was important to initially deduce it, right? So we could put the signs right for our accelerations. So the tensions cancel out here. 50, positive 50 minus 39.93 newtons is equal to 5.1 minus 10.19. kgs acceleration. Okay, so 50 minus 39.93, or 10.07 newtons, is equal to 5.1 minus 10.19. Negative 5.09 times A, right? Kgs, this is kgs, but it's whatever. And actually, so you don't want to get confused like I did over there, right? And become a bit messy. This is positive 5.1. When you subtract negative 10.19, what happens? You add those, right? This is going to be 5.1 plus 10.19. If you caught that, good job, but I almost didn't catch that. 5.1 plus 10.19. And that is around 15.29 times acceleration is equal to 10.07. and acceleration is equal to 10.07 divided by 15.29, which is around 0.65. So no, since it's 658, I'm just going to round up to 6 meter per second squared. Okay. And then obviously if you wanted to find the tension, I mean, you don't need to, but if you wanted to, then you could just plug this in here, right? Or any equation. I could plug it in the other one as well. I'll just plug it in here. Tension minus 50 newtons is equal to 10.19 kgs times 0.66. So tension minus 50 newtons is equal to 10.19 times 0.66. 6.73 newtons, because it's meter per second squared times kgs. So tension is equal to 50 newtons plus this. So approximately, and since this is negative here, always remember the negatives, right? Negative 6.73 newtons plus 50 newtons minus 6.73 newtons is, so that should be 43.27 newtons. Okay, and there you go. That's your answer. That's how you solve problems that involve dual incline pulleys. Okay, so try solving one more by yourself, this one, and then we could wrap it up and look at the other kinds of force problems that we might need solving. Okay, right, I'm assuming you gave it a try. Weight 1 is equal to 80 newtons, so weight 1 here. Weight 2 is equal to 60 newtons on a 45-degree incline joined over a peak pulley. Okay, so weight 1 here is 37 degrees. Weight 2 here is 45 degrees. Which way does the system move? Justify with the downslope components. Okay, so I need to find out which W sine theta is greater, because this is already mg, right? Mg sine theta is just going to be 80 newtons times sine theta. So, I mean, they already gave it. They didn't give us in mass. They just gave us in newtons, which means we have mg. 80 newtons times sine of 37. That's going to be 48.15 newtons. And this one is going to be 60 newtons times sine of 45. Or 42.43 newtons. Okay? Since this one is greater, the system is going to accelerate to the left. So this one is going to go down. Weight 1 is going to go down, and weight 2 is going to go out. Up, okay? Now we need to find the system's acceleration. So how are we going to do that? I can erase this so I have some more space. And then I'm going to write equations using free body diagrams for all of them, okay? For weight 1, tension is pulling me upward, but my negative acceleration is pushing me downward. Where's my negative acceleration? 80 newtons times sine of 37. Okay? And that's going to be equal to my net force, because there's no other force acting on me, right? Which is MA. Or, I don't have a mass yet, so I'm going to do 80 newtons is equal to mg. M is equal to 80 divided by 9.8. I was going to say 9.81, but you could just do 9.8. So this gives you 8.16 kgs. Right? So 8.16 kgs times acceleration. And this is going to be negative, since this is going in the negative direction. I'm going to define downward as a negative direction, okay? You could define it as positive, but I'm just going to define it as negative. So we could replace this equation with, if you simplify, tension minus, what is 80 times sine 37? 48.15 newtons is equal to negative 8.16 kgs times acceleration. Okay. All right. And then for the other one, tension is going to be pulling it upward, right? So tension is still positive. Weight is still negative because it's pulling it downward. 42.43 newtons, right? W sine theta, pulling it downward. But what is the acceleration going to be? Acceleration is going to be upward, right? This one is going to go upward because we determined that beforehand when we compared the W sine thetas. Since this one is going upward, that means this one is going to have a positive acceleration. So A times the mass, which is 60 newtons, is equal to m times 9.8. M is equal to 60 newtons divided by 9.8, or 6.12 kgs. Okay. And then, like always, we just subtract these two equations here. So I'll subtract this equation from this equation. Okay, I subtract these. The tensions cancel out. 48.15 plus 42.43. I mean negative 48.15 plus 42.43, right? So 42.43 minus 48.15, or negative 5.72 newtons here, is equal to negative 8.16 minus 6.12, which is negative 14.28 kg acceleration. So acceleration is just going to be equal to 5.72 over 14.28. These cancel out, the negatives cancel out, right? So 5.72 divided by 14.28, or 0.4 meter per second squared. And that makes sense, right? Because these are almost even weights, and when we calculated the W sine thetas, they were almost even. They had almost an even pull. That's why the acceleration is going to be slower, because they're balancing slowly, but not quite. Okay? And then if I wanted to find the tension here, I could just plug this into this equation, right? So tension minus 42.43 is equal to 6.12 times 0.4. Okay, so tension is equal to 2.448 plus 42.43, which should give me 44.88 newtons is tension. Okay. Now let's try one more conceptual problem. Two blocks on different angle inclines. Okay. This could be theta, this could be alpha, right? And then different angles, but the rates are equal such that it doesn't move, okay? So the W sine thetas are equal. W sine theta, so weight 1 sine theta is equal to weight 2 sine theta. Using Newton's first law, I explain why this system does not move at all. It doesn't move because since the weights are balanced, net force is equal to 0, right? And since they have a mass, net force is equal to mass times acceleration. Acceleration must be the one that's 0, because net force must be 0, right? So then, if it doesn't accelerate, that means it's not moving. The system's not moving. Okay? It could be moving, but at a constant velocity. And we know that they start at rest, so they're not moving. And objects at rest stay at rest, right? So they're not going to move either. And there you have it. Dual-Inclines, explained simply. Okay? And over here, next video, we're going to go over static equilibrium and how objects balance each other, just like how I was talking about the question there, but more examples of that in more cases, and how you can pull on two strings, but the object won't move. Alright, see you in the next video. Feel free to give me a like and subscribe so I can help others like you and make more content.